of scope in Jeli campus is netball court. So before we describe the problem that having here, let me introduce our group member. The first one is me, Nur Izzati Zulaika binti Syaiful Azwani, F22A0016, as the leader of the group. The second member is Muhammad Anur Fikri bin Idrus, F22B0024, as the editors for the group member 1 and member 2. So the third member is Abdul Al-Hadi bin Abdul Rizal, F22B0079, as the video manager. And the last member is Nurul Fadilah binti Nahru Shazwan, F22B0133. Unfortunately, the last member cannot join us because having heart problem. So I will explain the problem number 1, which is the width of the track that maximizes the total area of the court and the track combined. So the netball court at my university has the shape of rectangle with dimension 30 meters by 20 meters. The university is considering adding a running track around the court. The width of the track will be the same on all sides. Determine the width of the track that maximizes the total area of the court and the track combined. So the solution is, let's donate the width of the track as X meters. The dimension of the court with the track added will be 30 plus 2x meters by 20 plus 2x meters. The total area A of the court and the track combined can be expressed as A equal to 30 plus 2x times 20 plus 2x. So to find the maximum area, we can differentiate A with respect to x and set it to equal to 0.
Okay, so here the calculation is dA over dx equal to 30 plus 2x, and then 2 plus 2, 20 plus 2x. So we got we expand it, and then we got 4x plus 100 equal to 0. Whatever the division it, and we got a 0. So how we solve? This one equal to 0, so we must to find x. So 4x equal to minus negative 100, and then x, we got negative 25. So that's it.
However, since we are dealing with the physical dimension, the width of the track cannot be negative. So there is no solution to this problem. This means that the maximum area is obtained when there is no track added. In example, the court element has it.
The problem is the netball court in my university had the shape of a circle with radius of 15 meters. So the university wants to install the fence around the court to enclose it. So I need to determine the radius of the fence that minimize the cost of fence, given the cost is proportional to the length of the fence. Okay, for the solution for this problem is, let's denote the radius of the fence as r meter. The circumference of the circle, which represent the length of the fence, is given by c equal to 2 pi r. So the cost of the fence is directly proportional to the length of the fence. To find the radius that minimize the cost, we can differentiate c with respect to the r and set it to equal to 0. Means dc divided by dr equal to 2 pi equal to 0. since 2 pi is constant, it is never equal to 0. Therefore, there is no critical point for the radius that minimize the cost of the fan. In this case, the cost will minimize when the radius of the fan is equal to the radius of the cord. Means R equal to 15 meter.
The problem 3 is the height in meter of a netball thrown from the edge of the cord can be modeled by the function ht equal 10t minus 5t power of 2, where the t is the time in second. At what time does the netball reach its maximum height, and what is the maximum height? To find the maximum height, we need to determine the vertex of the parabolic function ht equal 10t minus 5t power of 2. The vertex can be found using the formula t equal negative b over 2a, where a and b are the coefficient of the quadratic equation. This case, a equal negative 5 and b equal to 10. Substituting this value into the formula, we get t equal negative 10 over 2 negative 5 equal 1 second. Therefore, the netball reaches maximum height after 1 second. To find the maximum height, substitute t equal 1 into the equation ht. h1 equal 10 1 minus 5 1 power of 2 equal 10 minus 5 equal 5 meter. Hence, the netball reach a maximum height of 5 meter.
For our group, thank you. Bye.